So good morning. So yesterday we continued our discussion of weak lensing, and we talked about the different statistics that one can measure in weak lensing. We saw that we can measure 2-point functions like the weak lensing power spectrum, and we saw that we can even do more advanced statistics, consider more advanced statistics, and get more information that is important for cosmology. We saw in particular that we can measure the power spectrum in different redshift bins, where we bin the galaxy into different redshifts. That's called weak lensing tomography. And we also saw that we can measure non-Gaussian statistics, and we described several non-Gaussian statistics based on either higher point correlation functions or other more advanced statistics. Okay? So first of all, before we proceed, is there any questions on this? Are there any questions? Okay. So then, let's talk about how we measure the shear. So in all this discussion, we assume that we can go from the images of galaxies to the shear. And then once we have an estimator for the shear for every galaxy, we can either, as we discussed, bin it into cells, into pixels, and make a map, or we can directly compute these correlation functions. So now let's discuss how one can get an estimator for the shear, okay, which is a crucial step in the weak lensing analysis. And in fact, as you'll see, it's actually not only a crucial step, but a difficult step, at least if one wants to achieve high precision. And there's a lot of work being done on this. So let me talk about all the different steps that go into this, or at least describe some of the steps done in some of the more simple analysis, and I'll describe some more advanced methods also qualitatively. So first, of course, the first step is to get data. And in order to do this, one needs a telescope, and one needs to go observing. So the great thing about working in astrophysics, especially if you do observational astrophysics, that you get to observe in very nice places. So I'd like to show this picture because to me it was particularly significant. This is the William Herschel telescope in the Canary Islands, which are islands off of the coast of Morocco. They are Spanish islands off of the coast of Morocco. It's really beautiful. There's a high mountain. There's kind of a volcano that collapsed. So you can have beautiful views of the sea and so on. It's a telescope actually at the time it was run by the British and the Dutch. This is where we did some of our first weak lensing measurement. Of course, there are other telescopes like this. This is actually a relatively old telescope. There are now much more modern telescopes, which I'll be showing you later. Now, in order to do the weak lensing measurements, one needs both very large, as much area of the sky as we can cover. So we get a large number of galaxies, which gives us more statistics. As you remember, the weak lensing effect is very small. It's only a few percent. So the effect on a single galaxy is very weak. So we have to average over as many galaxies as we can. And we also need to have as deep images as we can. By deep, that means very long exposure time, or as long as is practically possible, in order to, thank you, oops. In order to go for two reasons. One is to have as many detectable galaxies as possible, again, to get a large number of galaxies, and also to be able to go to as high redshift as we can. Because as we saw before, well, let me show you again on this plot, for instance. The lensing signal is expecting to be, the amplitude of the lensing signal is expected to be larger if the galaxy redshift is larger. Right? So if we go to higher and higher redshift, then the lensing signal is expected to be larger and larger, which gives us more signal to noise to work with, more information, and therefore more cosmological precision eventually. So one needs to go as wide as possible and as deep as possible, basically. All right? And that's only made possible by a new technology, which is large format CCD cameras. Okay, so CCD cameras are the detectors. I'll show a picture later a little bit more. These are basically digital chips that allows us to make very high precision images. And this is a technology eventually that led to the revolution in portable digital cameras that a lot of people have nowadays, or in your phone, for instance. Okay. So at the time, there was the cameras were made up of several chips, typically several thousand pixels by several thousand pixels. Now, as I'll show you later, we have cameras with many, many more chips, like 30 or 40 chips, which allows to cover even larger areas of the sky. So then one goes to a telescope like this. So you stay up all night, you observe. So if you have the opportunity, I strongly encourage you. You have some very nice telescopes also in India that you can observe with. And then, depending on the weather, you can get your data. Sometimes the weather is bad, so then you have to come back. But if you're lucky and the weather is good, then you can get your data. All right. So at the time, we used to go in individual observing sessions. So you would apply for time, get your time, go observing, come back, analyze the data. Nowadays, the amount of data we need is so large that we do it in a different mode. We do it in a survey mode. In other words, there are dedicated telescopes and instruments that are used, and it's big collaboration that run the observing by rotating the scientists on the mountain. So it's no longer individual small groups that go observing. Now it's a big collaboration which organizes this. And one gets images like this. Again, this is one of the images we use for the early weak lensing measurements. Here, of course, the white corresponds to low number of photons that detected, and the black corresponds to large number of photons detected. Like during the observation, one also needs to try to monitor the conditions very well. So what we need is the highest angular resolution possible. And on the ground, what is limiting is what is called the seeing, which is atmospheric turbulence that also affect the path of photons on the way from the galaxy, on the galaxy we're observing or the object we're observing, all the way up to here, to Earth. These tend to blur the images. I'll come back to that. So one needs to wait until the seeing conditions are good, and also that the instrument is performing. So there's quite a lot of optimization that are done during the observation themselves, because these are high precision measurements. So everything, a lot of parameters matter. So eventually we get images like this that cover large regions of the sky, at least several degrees. Now we are down to analyzing, as I'll show you, several hundred square degrees. And then if you zoom in a bit on the images, we get things like this, which doesn't look very impressive, because that's exactly the problem. I'll come back to that in a minute. But basically, all of these blotches are objects. Some of them are stars, so the very compact ones are stars. And some of them are more extended and tend to be and are galaxies. Okay, so the first thing to do is to take this image, run it through a software that can first detect objects, classify them as stars or galaxies, and then isolate and then, as we'll see, we'll need both the stars and the galaxy for our analysis, but eventually one need to turn the shape of these galaxies into an estimator for the shear. Okay. And typically, because we need to have as many galaxies as possible, we work quite close to the detection limit. So we have to use galaxies which are quite faint, like all of these little blobs here. Okay. Of course, the information in each of them is very small, but by averaging over a very large number, then we can recover the shear information. Okay. And that's really the trick part, and sort of where a lot of the work is going on in weak lensing, has been going on in weak lensing. So let me talk about what the problem is. So basically, let's think about what happens to the photons or to the image of the galaxy from the intrinsic shape of the galaxy all the way to what we detect. So this is what we call a forward process, right? There are many steps from the intrinsic shape of the galaxy all the way to what we detect that goes on both instrumentally and also in the astrophysically. And what we need to do then from that is estimate the shear. So let me go step by step. So here we start with the image of a galaxy, and let's suppose this is what it would look like in the absence of lensing. That's just a galaxy from the Hubble Space Telescope. It really doesn't matter, just for illustration purposes. Okay. So then this galaxy first gets lensed. right? So it gets sheared, it's distorted because of the weak lensing effect, and of course that's exactly what we're interested in, right? That's what we want to estimate eventually, okay? Then this image gets blurred by basically the effect of the atmosphere and the telescope, right? So as I said, there's turbulence in the atmosphere that tends to shuffle the photons around a little bit, on arc-second scales also, or a little bit less if you're in a good sight. All right, so instead of seeing the lensed image, we see the lens image but blurred by this atmospheric effect. And even if the atmospheric effect were not there, for instance, if we go into space, like with the Hubble Space Telescope or future telescopes, then the atmosphere is not relevant. But on the other hand, there's still a finite resolution for the instruments. Okay, so there's the telescope itself has finite resolution, and so the image gets blurred this time not only by the atmosphere and the telescope, but only by the telescope, which has a response function. And here, the way we characterize this effect is basically, you can show that it's basically a convolution of the image by a kernel, and this kernel is called, in optical astronomy, is called the point spread function. In other wavelengths, it has different names. For instance, the radio is called a beam, or in the microwave, it's called a beam, but in the optical, it's called the point spread function. What is the point spread function? It's basically the response of the instrument and the atmosphere to a point source. So let's suppose you put a point source, an unresolved source, okay, which is so small that it cannot be resolved. Then when you look at it on your detector, you're not going to see a point because it has finite resolution. You're going to see a function, and this is this function that we call the point spread function. And then if you have an extended object like a galaxy, well, you can show that what you see is a convolution of the intrinsic shape of the galaxy with this point spread function. Okay, so it's a convolution process, which involves, of course, the loss of information, because basically the image gets smooth and you lose the small scale information. And this point spread function can have structure, can have a complicated shape, and of course this needs to be taken into account in the analysis. All right, so that's the second step that the images go through as the light travels from the galaxy to us. And then the next step is that at the detector level, so all of this was the atmosphere and the telescope, but eventually the light gets focused onto a focal plane and hits a detector, which is, in this case, a CCD camera, as I was saying before. Now this detector has, of course, a finite pixel size. It doesn't have an infinitely small pixels. So we don't see this, but we see a pixelized version of this image, okay, because of the finite pixel scale. Okay, so now it's pixelated. And then, of course, also unfortunately, but that's in practice, that's of course unavoidable, at the detector, there's all sorts of sources of noise. There's noise coming from the detector itself, which has a finite read noise. There's also noise coming from the sky, the fact that the galaxy, the sky has some brightness, some surface brightness, and other sources of noise. So eventually what we measure is a noisy version of this. Okay, so you see, that's first the shear, the convolution by the point spread function, pixelization, and then noise. Okay, and this is what we measure at the end. Okay, and so the problem is to inverse this forward process and recover the shear from this. This is called an inverse problem. In this case, all the steps are they are lossy, so every time you lose information, well, from here to here you gain information, of course, because that's what we're looking for, but from here on, we're losing information at every step. So you cannot recover, there's no one-to-one recovering, you cannot fully recover the intrinsic image. But in these steps that we drew here, at least the nice thing is that they're linear steps. They're lossy, but linear, right? So if you double the intensity of this galaxy, then you double the flux at the end. There could also be other more complicated steps if there's some complicated effects in your detectors or on the telescope. That could actually be also some non-linear steps. But to a good approximation, the main important steps are all linear, which is a very important. So it's actually a linear inverse problem that we have to solve. Okay. Now, in order to do this, we of course need to know about the effect, some of these effects. All right? In particular, a very important one is this step here. Because if you take the lensed shape of the galaxy and convolve it with a point spread function, well, if the point spread function itself is not circular, for instance, which is the case in practice, then it might look like the galaxy has been sheared and the direction has been changed, but actually it's only the shape of the point spread function that you're looking at. So one needs to know is we need an estimate of the point spread function in order to correct for this step. And in order to do this, that's where the stars come in, because we also have stars in the image that we can use, and it turns out that the stars, so that's an example of a star. The stars have the physical size of the star with the resolution of this telescope is basically so small that they're basically point sources for us. And I told you that the point spread function is the response to a point source. So the stars act as a calibrator for the point spread function. So we can measure the apparent shape of the stars and get information about the point spread function. And the stars, of course, go through some of the same steps. So if you have a star here, which is effectively a point source, I don't know if you can see it, so it's a tiny little point here. It gets convolved, again, by the same atmosphere and the same telescope. Okay, so then its apparent shape is the point spread function of the measurement system. Then it also gets pixelated, and it also gets noisy as well. All right. So what we have here is measurements of the shape of stars that gives us a measurement of the point spread function. In practice, it's noisy and pixelated, so it doesn't have the full information. But nevertheless, we can use it to get a model of the star. Okay? Typically, stars, at least when we go to very faint, when we go to deep images, the stars tend to be brighter on average than the galaxies. So they tend to have a higher signal to noise of the galaxies. So it gives us quite a lot of information on the point spread function. Any questions on this? Yeah.
There seems to be a degeneracy between seeing and convolution because of the point spread function. So even if we determine the point spread function using a star, maybe when we use it to analyze galaxy images, the atmosphere may have changed.
Mm-hmm. That's a good point. So the point spread function that we consider here is actually is the combined effect of the atmosphere and the telescope. If we're on the ground, if we're in space, we don't need to worry about the atmosphere, right? So if we're on the ground, then what we call the point spread function is the combined effect of the atmosphere and the telescope. And for a given image, so it's not like we take an image of stars and then move on to make an image of galaxies. We use the same image, and in that same image, we measure the shape of galaxies and the shape of stars. So the stars are affected by the atmosphere at the same time, and so they give us a calibration of the point spread function, which is relevant for the galaxy. Now, the trick, though, is that that's true if the point spread function does not vary with position, right? So if the point spread function were constant across the image, then we take all the stars, we average, we're fine. The problem is that typically the point spread function varies across the image. So one needs to interpolate and make a model. And I'll talk about that, I think, a little bit later. Do I? Yes. And I'll talk about that a little bit later. But apart from this, since it's taken exactly at the same time, then that's not a problem. Actually, from time to time, we also go and move and make observations of star fields. So let's say there are places in the sky, like close to the galactic plane or around globular clusters, when there's a very large star density, and we can make dedicated calibration observations of these regions to get even more precise measurement of the point spread function. But then it's at a different epoch, and so the atmosphere usually have varied. But at least for calibrating the telescope part of the point spread function, then it's useful information as well. Yeah, but that's a good point. So the key point here is that we have stars and galaxies together on the same image that we use for measuring the shape of galaxies. In fact, we even optimize the observations in that way, because if you look at the sky, then part of the sky is occupied by the Milky Way, all right, our own galaxy, and there, of course, there's a lot of stars. In fact, if you look in the plane of the Milky Way, there's so many stars and many other things that you can't even observe through and measure the shape of extragalactic objects like galaxies. So if you move away from the plane, then the number of stars, the star density falls. And then if you move to the galactic poles, which are perpendicular to the plane, then the number of stars is much lower, right? So what we do is we actually use the galactic latitude, which is the angle between the plane and the pole, to tune the number of stars that we have in our image. So if we go too low, we have too many, we can't make a measurement. If we go too high, we don't have enough, we cannot calibrate. And we can go to intermediate regions, and there's a very nice band which is the most optimal for this, to get the optimal ratio of number of stars, number of galaxies to make the measurement. Yep. So that's one of the strategies we use. So there's some very interesting, actually, problems in optimizing the way you tile the sky, right? How many passes you make, how deep you go, whether you go close to the plane, off the plane, how you combine the constraints on the telescope pointing, and so on. That's called survey optimization, or survey strategy. And that's actually quite a complicated optimization problem that's done in large surveys. Yeah. To take all of this into account, to minimize both statistical errors and systematic errors coming from the stars, for instance, point spread function calibration. That's a good question. Okay, so we basically take the stars, measure the shapes, use that information to correct for at least this effect, and then we try to recover the shear. So how do we do this? How do we do this inverse problem? Well, it turns out that that's not a solved problem. There's been a lot of work and a lot of progress, and there are many different methods that have been developed to do this. And here I've classified them into several broad categories. There are subcategories and so on, but I won't go into it. Basically, the first category is what was used, at least the first methods that was used by the first method that were developed. One of the founding methods is called the KSB, after this paper by Kaiser et al., which I'll be describing a little bit later. It's sort of the first quantitative methods for doing this. It's actually still used after more extensive calibrations. And there the idea is to take the shape of to take an image of a galaxy and measure the moments of the light of the galaxy. And I'll show you how that works. So these are quadrupole moments that characterize the shape of the galaxy, and then correct for the point spread function convolution, and eventually get an estimator for the shear. And what I'll do is I'll describe this method in a little bit of detail to give you an example of all the other methods, because that's the simplest one to describe, and also it illustrates the fundamental steps that go into this measurement. Another class of methods can be called shape fitting. So here, instead of taking the image and measuring moments of the light distribution, one tries to fit a model to the light distribution. So we can take different basis functions and then fit these moments, fit these basis functions and get a model for the galaxy. And what we can do is as we fit, we can convolve with a point spread function. So if we have an estimator, a model for the point spread function coming from our stars, we can fit a model of the galaxy, which is convolved by this point spread function, and we compare it to the data and iterate or minimize the difference between the model and the data and get a model for the galaxy shape. And then from that, one can also get an estimator for the shear. Okay, and there's a lot of methods that have been developed using this approach. Okay, another interesting method which was developed at some point is called the stacking method. So here instead of measuring the shape of individual galaxies and then averaging them to compute statistics of the shear, one does the opposite. So we take the images and then stack them together. So we basically average the images directly. And then from that, we get an estimation for the mean shear. So instead of building an estimator and then averaging, one can average and then build the estimator. Okay, these are the advantage of boosting the signal or the information of the combined image before we make the estimator of the shear. So there's been some work on this with some success. And then another technique that we actually have worked on in Zurich recently quite a lot is what we would call a forward modeling method, which I'll talk about a little bit at the end. And the forward modeling method is basically it's based on the fact that all of these methods eventually need simulations, Monte Carlo simulations to calibrate them. So what people do in practice is that they run, so they make image simulations they make simulated observations, if you wish, where you know what the true shear is. You in the simulation you go through all the different steps, the point spread function, noise, and so on. You put this, so you basically simulate all these forward steps, and then you apply the method that you've developed on the simulations and check whether you get that the output shear, the estimator of the shear that you have, is equal to the input shear that you've put. And in the simulation, you know what the true shear is, so you can compare and you can calibrate the method. So here in this approach, the idea is to push that a lot further and base the measurement onto these on these simulations and make a very large number of simulations and make the simulations very, very fast, so that you can do this forward. You can simulate this forward process very fast and have loops in order to calibrate the shear measurement. Okay, and this is particularly important if some of these steps are not linear. Because then the inversion becomes much more difficult, and through the simulations you can calibrate even nonlinear processes, which turns out to be important at a certain level of precision. Okay, and as I said, a bit later I'll tell you more about this. Now, before I describe this, the KSB method, or at least the main ingredients of the KSB method, I want to mention that in order to check to test this method, there's been a number of what is called data challenges, which is a very interesting way to proceed. So basically, the weak lensing community set up a number of challenges. There had been a series of them. One was called STEP, grade 08, grade 3, and it's continuing. And the idea here is that somebody generates some simulations, image simulations, with some known shear in them. They don't reveal what the true shear is. They give the simulations they make it public to the whole world, actually, but of course it's mostly the weak lensing community which is interested in this. So they take these simulations, they apply the different method that they developed, they measure a shear, and then they give it back to the coordinators of the challenge, and then once everybody has given their answers, they compare with the true answer and they compare the accuracy of the methods. So it's called a blind challenge because the people running the methods don't know what the answer is. And of course, that's realistic because when we have real data, we don't know what the real answer is. And this allowed a lot of improvements in these methods over the years. Okay, and now the methods are starting to be quite accurate. Typically, the methods are accurate enough for the current generation of measurements, but when the next generation of measurement come with higher precision, then one needs to improve the methods even further. Okay. This kind of blind challenges is done in many other areas of cosmology. For instance, the cosmic microwave background, they organize also challenges to measure for different steps of the analysis. And many other probes do the same thing. It's a powerful way to proceed. Okay, so how does one do it in this KSB approach? All right, in this moment approach. So the idea is the following. Okay, so let's go step by step again. So the idea is the following. So first, one takes the image of a galaxy. Maybe I should have plotted on this graph too. So we take the observed image of the galaxy, right? And then we want to characterize the shape of the galaxy. First, we need to characterize the shape before we can even correct anything. We need a measure of shape. And one way to do this is to take the lowest order moments of the light distribution of the image that capture the shape information. And it's not very difficult to see that these are the quadrupole moments. So what are quadrupole moments? Well, they're basically a matrix, Qij, which is the integral over the surface of the image, so a two-dimensional integral of the image weighted by the moments, which is a product of the position, one of the position vector and one of the position vector here. Okay, so I can be 1 or 2, j can be 1 or 2. So this is a 2 by 2 matrix. And typically, which are basically gives you a measure of both the extent and the ellipticity of the source, as I'll show you in a minute. Okay. So why are quadrupole moments the lowest order shape information? Well, let's think about this, at least in terms of moments. So if we took the 0th order moment, so let's forget this W for the moment. I'll come back to that in a minute. So let's suppose this W is equal to 1, so it can be neglected. Then let's suppose we look at the 0th order moments. So in general, 0th order moment would be integral d2x times I of x times something which is a power to x to the 0, so it's basically 1. So it's basically the integral over the surface of the image of the intensity of the galaxy. So I is the intensity of the galaxy, or the image of the galaxy, if you wish. Well, that's simply the integral of the intensity. So that's basically the total flux of the galaxy. That's all it is. So the 0th order moment is just the flux, okay, which is interesting. But for lensing, that's not information we want to use, at least for the shear measurement. That's not the one we want. Then we can look at the next order moments. So instead of having power 0, we can have power 1. So we can have only one of these. Okay, so what is this? Again, let's forget this W here. So we would have integral d2x over the surface times x times I. Okay, so it's the integral of I times x. So it's a weighted average of the position, which is basically the centroid of the galaxy. So it tells us what the center is as weighted by the intensity. So it's sort of the center of the galaxy, which is something which is interesting and that we need. It's good to know the center, but this does not have any information on the shape. All right. On the other hand, if we move to one more power, so we look at the quadrupole moment, which is an integral of a square of these positions, then that has shape information, as I'll show in a minute. So for instance, let's look at the trace of this, which is basically x1 times x1 here, or you can do the sum, x1 times x1 plus x2 times x2, so you can do q11 plus q22. Well, this is basically x1 squared plus x2 squared, so it's basically r squared, so radius squared. So this is the integral over I of r squared, which is basically the average of the distance squared, which is basically the root mean square radius of the objects. So the trace of this gives us a measure of the size of the galaxy. And as I'll show in a minute, the off-diagonal element gives a measure of the ellipticity. Okay. One can form even higher moments, which will also have shape information and more advanced information. But for the measurement, so in order to capture the shape information, and in fact we will need the higher order moments, as I'll discuss later, but to get an estimate of the shear, the simplest thing is to use the lowest order moments that capture the shape. All right. Okay. Is that clear? All right. So now how do we get a measure of the ellipticity? I mean, after all, what we're interested in the shear is not the size, it's not the flux, it's how elliptical the galaxy is and which direction it's pointing. Well, what we do is we form what we call the ellipticity out of these moments. So we take these moments, which remember are Q11, Q22, and Q12. It's a symmetric matrix, so Q21 is equal to Q12, so there are three independent numbers. So it's a symmetric 2 by 2 matrix. And then we take combinations of them to form what we call the ellipticity. So in particular, we define what we call the E1, ellipticity, the first component of the ellipticity, or epsilon 1, which is basically Q11 minus Q22 over Q11 plus Q22. All right? So you notice that the fact that we're taking a ratio makes this ellipticity a dimensionless number. And also you notice that on the denominator here, we have Q11 plus Q22, which is this trace. So it's basically a measure of the size. And we divide by it to basically get rid of this information, which we don't want to consider. And then we take the difference between Q11 and Q22, okay, which is basically a measure of the part of the traceless part of this matrix. And then we define an ellipticity, second component of the ellipticity, epsilon 2. This time we take Q12 over Q11 plus Q22. Okay? All right. So what does that mean? Okay, we can always do this, but what does it mean? Is it useful? Well, the answer is yes, and it's illustrated in this diagram here. So if you look at this diagram, this is basically a two-dimensional diagram that shows the two components of the ellipticity of a galaxy. So every galaxy is assigned an ellipticity which has two components. Okay, so every galaxy is going to be assigned a position on this plane. And depending on this shape, it's going to have different position on this plane. So for instance, if the galaxy is circular, then it's easy to see that if it's circular, there's no special direction. So Q11 is equal to Q22, so E1 is 0. Q12 is also 0 because Q12 corresponds to an elongation at 45 degrees. And so this is 0, so the galaxy would be assigned 0 ellipticity. So if the galaxy is circular, you get 0 ellipticity. And then if the galaxy is elongated along the x direction, like here, you get a positive E1 ellipticity. If the galaxy is elongated along the y direction, then you get a negative E1 ellipticity. And then if the galaxy is elongated at 45 degrees of the x and y axes, then you get a positive E2. And if it's elongated in that direction at 45 degrees, then you get a negative E2. All right? So you see that the ellipticity tells us both how much the galaxy is flattened and in which direction, basically. Okay? So the more flattened it is, the higher the ellipticity is. And the ellipticity goes from 0 to 1, 1 being an infinitely flattened galaxy. So really the ellipticity has basically two numbers. You can recombine them if you want. One is the amplitude of the ellipticity tells you how flattened it is, and you can also get an angle out of it that tells you in which direction it is. All right. Yeah.
Pi for circular E2 is 0.
Sorry?
Pi for circular E2 is 0.
Why is E2 0? Because if you look at the integral of basically x times y, or x1 times x2, if it's circular, this would average out because the galaxy is symmetric about the x and y axis. So you're going to get 0 here. So you only get non-zero, if there's a correlation between, if the galaxy is flattened along the x and the axis perpendicular to the x at 45 degrees compared to the x and y axis. Okay, you can, if you want, you can try and work it out. Yeah. Okay. All right, so then we have this ellipticity, good. So that starts looking more like the shear, right? Because what we've characterized, we have the lowest order information about how flattened the galaxy is and in which direction. We even got rid of the size information that we're not interested in this particular measurement by dividing by the trace, which is the information about the size. So that starts to look good. And then the question is, what's the relationship we get with the shear? And one can show, and that's the crucial step, one can show that there's a relationship between the ellipticity and the shear. So let's suppose we start with galaxies that are randomly oriented, okay? And then we apply the same shear to all of them, just for the moment thinking about the pixels, averaging over a pixel for the moment. Then what happens is that if you can easily show, well not easily, but you can show, it's not that hard, that if you take the average ellipticity of these galaxies to which the same shear was applied, then what you get, so if there's no shear applied, you get 0 because the galaxies are randomly oriented. So on average, they don't have a special direction. So the average ellipticity is 0. But if a shear has been applied, what you get is something proportional to the shear. So what you get is the shear, which is gamma, times a factor here, which actually can be a matrix, which is called the susceptibility, shear susceptibility tensor. And basically, to at least to lowest order in the shear, so here you assume the shear is weak. So to first order in the shear, you get that the average ellipticity is equal to the shear times the susceptibility tensor. Okay? And I remind you that the shear is defined like this. So this is a distortion matrix. Remember the derivative of the image, of the position on the image compared to the position of the source. And the shear is the traceless part of this distortion matrix. Okay. So then, if we know the susceptibility tensor, then we can invert this and get an estimator for the shear. Okay? And one can show that the susceptibility tensor can be expressed in terms of the higher order moments of the source, the octupole moments in particular. All right? So one needs to measure not only the quadrupole moments, but the octupole moments, and then we can get an estimation for the susceptibility tensor, and then from the ellipticity we can get an estimator for the shear. I'll show you that in a minute. Okay. All right, so that will be fine, and in fact the algebra is not too difficult as long as we ignore this W here, and then you can find an expression for this P gamma, and it's not that hard. The difficulty comes in the fact that in practice we have to introduce this W. So what is this W? Well, W is a window function that we use as a weight inside the integral for measuring the quadrupole moments. So why do we do this? Well, the problem is that, and you can also show that if this image, if you add noise to this image, so if you do this integral here of I plus some noise, okay, if you don't do anything and integrate to infinity, right, on the whole plane of the image to infinity, then the error on the quadrupole moments diverges. And the reason is because we are doing an integral weighted by r squared, basically, and so that weights the regions far from the center heavily, and that makes the noise diverge. So in practice, one cannot do this integral out to infinity, so we need to either cut it off at some limit, or more conveniently, rather than cutting it off with a hard limit, we basically add a window function that tapers it off. And typically this window function is a Gaussian whose size is chosen to be close to the size of the galaxy. So we basically cut off the integral at large radii with a cutoff, a smooth cutoff function whose size is comparable to the size of the galaxy. Because beyond the galaxy, of course, we have noise, so that's not interesting. So we cut it off. And that is necessary, but unfortunately makes this P gamma factor more complicated and involve these octupole moments and so on in a more complicated way. But it still can be done analytically. And this Kaiser Square and Broder's paper, KSB, were the first ones to work that out. Okay, is that clear? All right. Now, the only thing is that this assume that this is the ellipticity of the galaxy after lensing, but that does not take into account the convolution with the point spread function. All right. So before we can do this, we need to correct for the point spread function, and then we can use this relation. So how do we do this? Well, as I said, what really makes it possible is the fact that we have stars in the image. So what we do is we take the image and we detect the stars, and then we compute, just like we do for galaxies, we compute the ellipticity of all the stars, okay, which gives us a measure of the ellipticity of the point spread function. We also can measure the size of the point spread function using this technique, using the moments. Okay, and so each of these little lines here corresponds to one star found in one of the weak lensing images that we used. And then each of these bars correspond to the ellipticity of the star, so it corresponds to an estimation for the ellipticity of the point spread function at this position. And you see, as I was saying before, that this is not constant at all, and this is quite typical. The point spread function typically has patterns. These patterns change with time. Some of it arises from the atmosphere, which has different patches. Some of it is the telescope, which has different geometrical optical effects. The part of the telescope tend to be more stable, but is not perfectly stable, because the telescope can have a flexure, so it can have mechanical stresses on it. In particular, there's some effects, especially on older telescopes, of flexure as due to gravity. So if the telescope points this way, it's mechanically not in exactly the same state as if it points downwards, because the gravity acts differently on the different parts of the telescope. The more modern telescopes are much stiffer because they're made of more stiff material. Again, some very interesting technology comes in here. And so this pattern is not constant, but it can be modeled. So if we have tuned by using the galactic latitude, the number of the star density on the image, then we have enough stars, and then we can map it, basically, so using all these measures. So you see it still has a smooth pattern. So what we can do is we can model this ellipticity pattern of the point spread function, and then with the models, the different ways of doing it, by smoothing, by fitting, by many other things. Then we can subtract the model from the observation of the stellar ellipticity and look at the residuals and check that they're very small and consistent with the error. So basically consistent with 0. Okay, so this is an example of the residuals. Now the difficulty is that the typical ellipticity of the point spread function in this case is quite high. It's kind of 5 to 10%, which is, remember, that's 10 times more than the signal we're looking for, which is more like 1%. The shear is 1%. These were from early images with old telescope like the William Herschel, which was not designed for weak lensing measurements. Now the telescopes, the more modern ones, have more ellipticities of the order of 1% or so, one order of magnitude lower, but nevertheless comparable to the shear signal we're looking for. So this step needs to be done very, very carefully. And there's a lot of cross-checks to verify or to test whether there's any residual error in this modeling. Okay, so once we've done this, then we can then use that measurement or that model for the point spread function to correct for the PSF. And one can show, again, Kaiser Squares and Brothers, 95, this KSB paper has shown how one can do that. And they've shown that, again, so a little bit of algebra, but not very difficult, that basically you can get a corrected, you can get the true ellipticity of the galaxy after lensing from the observed one. So you can get the ones before the convolution of the point spread function, which is the one you want, is equal to the observed one, so the one that you see after the convolution for the point spread function, plus a correction term, which is proportional to the ellipticity of the star, ellipticity of the PSF that you have in your model, times some factors which are called smear susceptibility tensors, which are measured from moments of the star, of the point spread function, light image, and moments of the galaxy. Okay, so you can measure these higher moments, compute these susceptibility factors or tensors, multiply it by the ellipticity of the point spread function that you've measured, and then correct and get the galaxy ellipticity before corrected for the point spread function. Okay. And then once you've done this correction, you can take the inverse of this susceptibility factor. Sometimes you have to invert it as a matrix. Sometimes it's enough to do it as a scalar. That's a kind of technical detail. And then you get an estimator for the shear. So at the end of this process, for every galaxy, you get an estimator for the shear. Okay? So this estimator is noisy. So the amount of information on the shear per galaxy is very small because the galaxies are faint and because the shear is very weak. But if you've calibrated your method properly, if you average over a large number of galaxies which have been sheared in the same way, then this estimator should give you the true shear that you've done, that was applied. Now the problem is, in practice, there's all sorts of errors in all these different steps. And as a result, there are still typically left some systematic errors. So the shear estimator, when averaged, doesn't quite equal the shear that's been put in. And that's where the simulations come into play. and you use the simulation to calibrate, and you improve the methods until it's robust and so on. Okay. As I said, there's still a lot of work going on with this, but now the improvements of the method is quite impressive. Okay, are there any questions on how we can construct this shear estimator?
How do we get the speed out of that?
So the P gamma factor, one can show, I didn't write the equation, it's a bit cumbersome. Hold on, can I? Oh, I didn't do this. The P gamma factor, you can show that you can express it in terms of the quadruple moments of the galaxy shape and higher order moments. And you have to go all the way to octuple moments. Right? So if you measure all these moments, then you can get an estimation for this P gamma factor. So in principle, it can all be estimated from the image itself. Okay. The difficulty is that these higher order moments are even harder to measure, they're even noisier, and so typically there are some biases or systematic errors in the measurement of this P gamma and the estimation of this P gamma. That's where the problem is. Because here you need to measure a moment, let's say the octuple moments would be 4 powers of x, which are even more weighted, they go even faster. They made it weighted even more strongly as a function of radius, and so they're even more susceptible to the errors coming from the noise, and many other errors as well. Okay. So that's one of the difficult parts in the weak lensing measurements. And then once you have it, you can invert it and you get your shear estimator. Any other question? Okay. All right, so now that we have seen how we can go from an image to the shear estimation, and then we saw how we can go from the shear estimation to either maps of the mass or statistics of the shear field, like the power spectrum, for instance. Then we have now seen all the steps. And then the question is what people have managed to do with this technique. Okay, so what is the status of the observations? So I'll start and then we can probably continue tomorrow. Okay, so this topic of weak lensing by large-scale structure is actually a very old, it's been worked on for a long time. So sometimes we call this cosmic shear. Okay, so what cosmic shear is weak lensing on large scales, as opposed to weak lensing by individual clusters of galaxies, for instance, right? So I also showed you can take a cluster of galaxy, use the weak lensing technique, mass its map, and so on. But for the cosmological application that I'll be discussing, what is more relevant is measuring weak lensing in large fields, like I showed you on the simulations. Now, for clusters of galaxies, the weak lensing signal is larger because, of course, the mass concentration is larger, the lens is stronger, and it's typically of the order of 5%, between 5 and 10%, while in a typical region in the sky, as I said, the weak lensing shear is more like a few percent, so it's even lower, so even harder. Okay. So there's an interesting history for this weak lensing by large-scale structure measurements, or as I said, cosmic shear. And actually, you can trace this topic back to a lecture by the famous physicist Richard Feynman. Who has heard of Richard Feynman?
Who has not heard of Richard Feynman?
Well, yeah. But if you ask positively, if you have negatively, people don't dare to respond. Right? If you ask who has not heard, nobody's going to say yes. If you say who has heard of Richard Feynman, so who's heard of Richard Feynman? Yeah. Now people are afraid of not saying yes. Okay, but it's less so. Okay, that's a trick when you teach. You always ask the question the other way around because otherwise you don't get the right answer. Okay, so Richard Feynman was a very famous physicist who invented various things, a very major development in quantum field theory, in particular development of quantum electrodynamics and many other things, including things about the space shuttle. And he has a lot of entertaining books. He has very interesting textbooks that you can look at as well. And he worked on, obviously, a very large number of topics. And in fact, he gave a lecture in 1964, I've been told. I wasn't there. I'm not that old. But, you know. So I've been told the story that in 1964 he gave a lecture where he was at Caltech. And what he said in his lecture is that he thought that because of inhomogeneities in the universe, the shape of galaxies should have some weak coherent alignments, which is basically the entire principle of weak lensing by large-scale structure. He gives this lecture. He also makes some estimation how big it is. Now, at the time, of course, the cosmological model was not as precise as what we have now. So these estimations were, of course, relevant only for the model they had at the time. But some people, he never published it, apparently. But there were several bright people in the room. So one of them was Jim Gunn, who told me the story, but there are many others. And then from that time on, there's a stream of theoretical papers that tries to compute the strength of this effect, which we now call basically the weak lensing power spectrum, the strength of the lensing. So basically what we now know is about a few percent level. So the stream of theoretical papers from the 60s all the way up to the 2000s or so that estimates the strength of this effect based on the cosmological model that they had at the different times. Okay, so better and more modern cosmological models. And actually, some of these papers are very interesting to look at and to read. And eventually, there were calculations in our lambda CDM model, which give us a few percent and the power spectra that I showed you. Okay, the question. But as I said, the measurement is very difficult to measure because now we know it's only a few percent. So it took basically 40 years or 4 decades before it could be convincingly detected. Right, from this lecture in '64 by Feynman all the way to when it was detected in the early 2000s. And what made it possible is a technological breakthrough, which is what I was telling you before, which is the advent of large CCD cameras. Okay, and this is an example of one of them. This is a subprime cam on the Subaru telescope, which until recently was one of the both larger and also precise cameras. There are many others. And what you see here is the focal plane of the camera. So this is placed at the focal plane, at the focal surface of the telescope. So the telescope would focus the beams and form an image. And then the image is recorded by this camera. And you see that the camera is made up of different chips. Each of these is a chip. And each of these chips have a very large number of pixels, typically several thousand by several thousand. Okay? And then, so first there was the breakthrough, the technological breakthrough of making large format CCD chips with large number of pixels. And then the other breakthrough was to be able to make mosaics of it with a very careful alignment, with multiplex electronics to read them fast and efficiently and form these large cameras. And as I'll show you later, there are even much larger ones now. And this development driven by astronomy has led, as I said, to the revolution in digital cameras that we'll have. Now they're based on other technologies, but some of it arises from this. Okay, and if you remember, the reason why we need such large cameras is both to get enough. So basically, we need a large number of galaxies. So we need wide format, large number of pixels, and wide format telescopes. We need to go deep, so we need to go as faint as we can, so they need to be very sensitive, so they need to have good efficiencies. They need to be on big telescopes, so we can gather light fast enough to go deep. And very importantly, they need to have very good image quality. So before these, what were people doing? So do you know how people were doing visible astronomy images before CCD cameras? Anybody know? You're too young to, of course, have been witness it, but do you know what was used before as the technology?
Photographic.
That's right, photographic plates. And these were quite impressive. I mean, you can still go and see them. They were very big, like photographic plates that big, that were put at the focus of wide field telescopes. and they were making quite good images. In fact, for a while, the photographic plates were better than the early CCDs in image quality. Okay, it's always the case that the last technology at the end has been worked on so much that it's still, for a while, it's still better than the new technology coming in, which had all sorts of problems, all sorts of image defects, and so on. But eventually, the CCDs took over completely, and now it's all done with CCDs. And the photographic plates, the advantage of them is that you could get very large formats, because all you had to do is print a large photographic plate, while each of these, as you can imagine, is very expensive and hard to make. But the problem with the photographic plate is that they are non-linear. Okay, they're quite linear, and for the purpose of astronomy before, in early time, that was perfectly fine, but they're not linear enough to make these weak lensing measurements. Okay. Now, what people did after doing photographic plates is they still took photographic plates, but then they digitized the image of the photographic plate using laser scanners. That was already an improvement, because at least we had digital images. In the past, you actually had to go. So if you go to Cambridge, the library, for instance, I don't know if they still have it, but you had these huge rooms with enormous images. So if you had to go observing, or you wanted to know about a specific object, you would know its position in the sky, and then you would go to the library, pull out an enormous image, put it on the table. It was quite nice, but took a long time. And then you would go find the position, take a magnifier, say, look what it looks like, make some measurements, and so on. That was before computers, right? And now, of course, so the first step was to digitize these images, so you could have all of this digitally. And then the next step is now it directly comes out digitally into a computer, and is immediately sent to the science team, which can be all over the world. Right, so your generation doesn't know what all the difficulties of the previous generation. We have other difficulties, but at least we don't have these. Okay, so what I'll do tomorrow is, and I'll tell you the different measurements that have been done, a little bit with history, but mostly the most recent state-of-the-art measurements that are done with these cameras. And then I'll also tell you what the future looks like with future instruments that will improve even more these measurements. So we'll do that tomorrow. So for every galaxy, so you have a given galaxy, right? Okay, so you have an image of that galaxy. Okay, some image of the galaxy. Then through all the steps we described this morning, correcting the PSF and everything, we get an ellipticity for the galaxy, and then we correct, and we get an estimator for the shear. Let's call it gamma hat. Yeah? Correcting for the point spread function, measuring moments, and so on, right? So for every galaxy now, we get an estimator for the shear, for that galaxy. Okay, and then, so that gives us a catalog for every galaxy. We get a long catalog of all the shear estimator for every galaxy. And then we can take pairs of galaxies, we can select. So if we have a big region, we have one galaxy here, one galaxy here. This one gives us an estimator for the shear. This one has another estimator for the shear. This is for this galaxy, let's call it A. This is for galaxy B. Okay, now we can take pairs of galaxies, and we can form these correlation functions. Okay, C1, 1, for instance. We can take the average of all pairs of the estimator of the shear, let's say gamma 1 for galaxy A, and the shear estimated for galaxy B. And we average over all galaxy pairs which have a given separation AB equals to theta. Right? So we can pick one pair, get the estimator for that one, the estimator for that one, take the product, and then we can take another pair which have the same separation theta, and then we get another pair, and then we compute the product, and then another pair, and average of all pairs, and that gives us directly a measure of the correlation function in that, as a function of theta for that bin, for the shear, and we don't have to go through a step where we pixelize, so we don't have to go and make little averages inside a pixel. We skip that step in practice. We could do it like that. We could also do it, but as I said, this would smooth the field, and we would not be measuring the correlation of the function of the shear will be measuring the correlation function of the shear smoothed by that pixel function, which you usually don't want.
So all the physics of detecting that there is a distortion goes into the shear estimator.
Yes. So in the shear estimator, you correct for all the instrumental effect, and you correct for the you divide by the susceptibility to the shear, so that on average, this correlation function. So each of these give you an estimator, and then if you average over a large number of pairs, then you should get the correlation function.
So the mechanism by which you're detecting that there is a distortion was in pixelization. It was correlation of shapes of different objects.
Yes.
While here it is using a point spread function.
No, it's the same. It's the same. So you take all the image of galaxies. For each of them, you get an estimator for the shear. And then either you do what I just said, or another way is to look at your image and make pixels. Right? Look at all the galaxies inside the pixel. And instead of doing the average of the pairs like this, you just take the average of the galaxy, of the estimator of the shear in that pixel. Okay, so for that, you pick that pixel, you look at all the galaxies inside that pixel, and then you average the shear here. That gives you an average shear here, an average shear here, an average shear here, and you make a map. Okay, and in this case, if you want to go straight to the correlation function, instead of averaging the shear in pixels, you average products of shear directly to get the correlation function.
So I understood it wrong earlier. I thought that within a pixel, the correlation of the shapes is what is used to infer the shear.
It is. Right? So inside the pixel, okay, so if you look at one pixel, and you looked at the shapes of galaxies if you have no lensing, on average, there will be 0. Yeah? But because there's a lensing effect, there's a coherent alignment of the galaxies in that pixel, and so they will be somewhat oriented towards the shear, in the direction of the shear, and by measuring the average ellipticity or the average shear estimator, you're going to get a non-zero value. Okay, it's because they're coherently aligned together in that pixel that you get a non-zero value for this shear. Okay? And it's the same effect here, except that here, instead of making a map and looking at individual pixels and mapping the shear, you're doing straight into the two-point function of the shear. So you're looking for correlations of shapes also. So this will be if the shapes of the galaxies, so if you take two galaxies, these two, if these shapes are not correlated, which means if there's no shear, then this product will be 0. Because if there's no correlation, the average of the product is a product of the averages. Right? And then this will be 0 because the average of this is 0, the average of this is 0, so you get 0. So if there's no correlations induced by the shear, you'll get 0. But if they are correlated, then you're going to get a non-zero signal here. So it's the same thing, except that it's two different ways of characterizing the same signal. One, you average over cells and you make a map, and the other one, you directly go to the two-point function. But it's the same thing. I was illustrating it in the beginning with the pixels because it's easier to understand. Okay? But in practice, to measure the correlation function, you skip the pixels step. Now, for instance, if you want to measure the power spectrum of the lensing, there are different techniques of doing it, but sometimes one goes through pixels there too. So you pixelize, you make basically a map, and you compute the power spectrum of the map. So sometimes you actually go through this step, but sometimes you skip it and you go directly there. Okay, and the fact that if this is an unbiased estimate of the shear, if you've done your correction of the PSF and everything right, then this should also give you a unbiased measurement of the correlation function. Yeah. I'll talk a little bit more about what it means for these to be unbiased and how good an estimator one needs. So it turns out for a given survey, one can write down requirements for the systematic biases of the estimator. And I'll be talking about that. So for a given precision you need to reach, this estimator needs to be, has a bias which is smaller than some level. And now it's very well characterized. And so when we test our shear estimator to test our weak lensing shear measurement pipelines, then we compare it to the requirements and check that it works within these requirements. So is that clear? Or?
But I think that method is more practical, no? Because the number of galaxies are quite a lot, and means every time I.
So
means what I feel.
Very good point. So here the advantage of this one is that you are just averaging over galaxies, right?
Yeah.
So this is linear in number of galaxies. You take your list of galaxies and you put them in pixels in your average, and then you get the map.
Yeah.
And then if you do a power spectrum, then you can use a fast spherical harmonics, a fast Fourier transform to do the power spectrum. It typically goes like n log n, so it's still relatively fast. Now this one you have to average over pairs of galaxies.
Yeah.
And that's much more. That goes like n squared,
Yeah.
right? So that's much slower. But so in the beginning, people could still do it because the amount of data was small enough that one could still do this. It takes longer, but you can still do it. And this is more direct, so there's less of processing, so it's potentially less biased, so it's interesting. But now this is getting with the current service, this is getting very cumbersome, so that's a very good point. And there are two ways to go about it. Either you do this anyway, but you use clever algorithms, like tree algorithms, to reduce the computational complexity and the computation time of measuring the average of pairs. What's also expensive is to look for pairs, right? To find the neighbors. It takes a lot of time, so you can use a so-called tree algorithm to do this. And instead of going like n squared, it's a bit faster. And they're pretty efficient algorithms now. Or you do directly there. You go here, you do a map, and then you can use fast Fourier transforms and get the power spectrum out of it. And more, we're moving into that direction. But I'll show you results which does both, actually. But that's a good point.
But when you pixelize, there would be a limit. There would be a constraint on the scale to which you can probe.
That's right. Yeah, because clearly you've smoothed basically on the scale of these pixels, so you cannot probe scale smaller than this. So you've lost information, and it's even slightly worse than this because typically you can have areas of the surveys which are corrupted by missing data, or there's a bright star that you have to mask out. So there are some masks typically, that you cannot use. Let's say that data is bad. So some of the pixels have only partial information. So that's called a masking effect, and that needs to be taken into account, and that adds complexity. Even the edge of the survey, which are typically not regular, they typically have complex boundaries. They don't fall exactly at the boundary of pixels, and all of this has to be taken into account quite carefully, and that you have to calibrate, make sure you don't have any biases. While if you go directly to pairs of galaxies, it doesn't matter, because if you don't have a galaxy here, you never have to worry about it, and you don't have to worry about this masking effect. So this is a much simpler, more straightforward, but slower analysis, and this is a much faster, but where you have to be a bit more careful. And there's still a lot of work on this. The cosmic microwave background measurements use this. They pixelize first on the sphere, and then they have a lot of techniques to estimate the power spectrum on the sphere. And also they take care of the mask and everything. So now, because the surveys are becoming so big, we're starting to import techniques from the cosmic microwave background to do these measurements. I'll show you actually results on this. We have a student ETH who's done this in particular, for instance.
Also for this method, pixelization, we need the distribution of the Lensi medium to be very smooth, right? Otherwise it might depend on how we choose our grid. If it's not smooth.
Well, if it's statistically homogeneous and isotropic, right? If it's statistically, you will get the same answers if you looked at different regions, then the only effect this pixelization has is to smooth the field. So if it has a lot of small scale power, which is what you're talking about, then it'll get smoothed out by this pixel scale. So actually it will help, because you would remove the very small scale power, the very, rough nature of the shear field. But in practice anyway, the shear field is relatively smooth, so it doesn't matter that much. You lose information. If you didn't pixelize, you could go and get information on even smaller scales. But the field is relatively smooth, at least in the weak lensing regime. Of course, in the strong lensing, there's a lot of power on small scales, but that's only a very few places which are subdominant in an analysis like this. Any other questions? Yep.
Sir, in CMB power spectrum, we usually observe late time ISW effect.
Yes.
Do we have anything similar in weak lensing power spectrum?
So that's a good question. So in the cosmic microwave background, let me see if I found finally my slides. Yes, I did. Okay, so yeah. So in the cosmic microwave background, there are actually a lot of very interesting physical effects that we can use to probe cosmology. The one I mentioned is the primary source of information, which are the fluctuations coming from the last scattering surface that we can measure, and we can measure the power spectrum and get the cosmology. Now there are secondary contributions as well. For instance, the ISW, integrated Sass-Whorf effect, which is the fact that the temperature of the cosmic microwave background get affected as the photon travels between the last scattering and us, if the gravitational potential evolves as a function of time, which is the case in models where there's dark energy, for instance. And that can also be measured, and actually it has an impact on the power spectrum of the microwave background. And that is sensitive to large-scale structure at relatively low redshift, which are the same structures probed by the weak lensing survey. There are other secondary anisotropies, so we call them secondary anisotropies, which are also produced at low redshift. There's the Zhuniev-Zeldovich effect coming from the hot gas. There's actually lensing of the cosmic microwave background itself, which we'll talk about a little bit later. But these microwave background fluctuations are also being lensed by we discussed this over the tea break. They're also being lensed by the same structure that produces the lensing of galaxies. This effect is quite small and hard to measure, but now it's been measured very well. In fact, you can do weak lensing with the cosmic microwave background. I'll show you that a little bit later, and several other sources of secondary anisotropies. And these also allow us to probe the large-scale structure at relatively low redshift, and they're very interesting. And they can even be combined with the weak lensing measurements or galaxy surveys. And I'll be showing some of that tomorrow. Actually, it's getting very rich because we can probe the same structures through many different physical probes that probe them in a different way, and that gives us a lot of information. So that's a new. There's a lot of work happening right now on this.
You are saying a cross-correlating ISW with the weak lensing?
Yeah. So you can cross-correlate the CMB with the weak lensing, and that will pick up several things, including the ISW effect. It can also pick up SZ.
Can beat the cosmic variance also?
So no, because you still only have finite number of cross-correlating modes, so you don't beat cosmic variance, unfortunately. So it's still pretty weak, but you still get an interesting constraint. I mean, it's so you get that too. Yeah. So that's a very rich new subject. You can also compare the lensing from the CMB and lensing from galaxies. And then you can help calibrate the two measurements, get more information. And now people have started doing it. The signal is still weak, but I'll show you tomorrow a very recent measurement of this. Yeah. It's very, very interesting area. All these cross correlations between all the different probes. Yeah. You had another question, or that was it? Any other questions on extensions or questions on Anjan's lectures? It's all clear, 100% clear. You understand structure formation completely? Your lectures are so clear that there are no questions.
Or they could understand it.
Or nothing. Yeah, either they understand nothing or everything. Okay. All right.
So I had a question.
Yeah.
You said that in these pixels things are perfectly aligned.
Not perfectly. They are aligned on average. So it's still noisy. They're not perfectly aligned at all because each galaxy has an intrinsic shape, okay, which are completely random. So that adds noise. But there are still some correlations in their alignment that we can measure by averaging. But they're not perfectly aligned.
Why should there be correlation with the alignment?
The correlation is coming from the lensing. It comes from the fact. So if you look at a small patch, so you see it's easier to think in terms of pixels to explain this, but actually you can do it with a correlation function. If you look at a small patch, in the absence of lensing, you would have galaxies in various random directions. Okay? Because galaxies form and they're over a very large redshift range and they're all over the place, right? And then because of lensing, what you're doing with lensing is you're stretching all of them in one way. So for instance, let's suppose the shear is in this direction. You would be stretching them a little bit this way and compressing this image a little bit this way. So all of them will get compressed. So if you had, I don't know if there's another color, but all of them will look a little bit distorted like this. So they will still are mostly elliptical because of their own shape, but they're all a little bit compressed like this. So if you compute the mean ellipticity of the galaxies without lensing, it would be 0 because they're randomly oriented. But because of the lensing, they tend to all be a little bit aligned into the direction of the shear. And that's what we're picking up. So this is this, it induces these weak correlations in their shapes. An example I was giving is that if you've ever been swimming in a pool and you can wear a mask, right? You go in the bottom of the swimming pool and you look, let's say, at a tree outside, okay? And you look there and you see distortions because of the waves at the surface of the pool, right? So you're seeing the tree and the leaves of the tree, but they're all distorted because of the waves of the pool. So if you look at a few leaves in some region, they're all going to be distorted in the same way. Another region will be distorted in the same way because the waves are kind of coherent on these scales. And that's exactly the same thing as lensing, actually, right? It's as if you're looking through, either water with waves or glass or glasses or something like this that distorts the image. And in the given region, they should all have a distortion in the same direction because they all lens by the same structures.
So for the point spread function, we use the images of stars.
Yes.
So are we able to resolve stars outside of our galaxy?
No, so outside of the galaxy we cannot, I'm not sure if we can resolve stars outside of the galaxies, but we don't need to. So we use the stars that are in our galaxy.
So how does it...
All right, very good. So what does our galaxy look like? There's a disk, there's a bulge, a disk, and there's a big dark matter halo. And we're sitting here about 8 kiloparsec away from the center of our galaxy. And in the bulge and in the disk, there are stars all over the place, right? So in particular in our neighborhood, there are lots of stars. So if you look into the direction of the center of the galaxy, you see lots of stars. You can't see anything, you can't see through. So we don't do that. But if you look, let's say, out of the plane of the galaxy, let's say in this direction, you can look at a galaxy outside our own that you can use for lensing. It gets lensed, right, by structures along the line of sight. But in that direction, there are stars in our galaxy. So if you look in that direction, you're going to see the distant galaxies outside our own and a lot of stars from our galaxy. And these are the ones you use, actually. So the stars are in our galaxy. And there are many of them. And of course, as I was saying, if you look in this direction, you're going to have too many of them, you can't see anything. If you look up, you have few, and you don't have enough to calibrate your PSF. But if you look at some intermediate angle, then you have enough. And so we can tune the angle to tune the number of stars that we use. But we don't use the stars which are in the distant galaxy. These are not resolved typically.
So from this point spread function of the stars that are in our galaxy, can we use that to infer the shear of galaxies?
No, because you can only use it to probe the effect of the atmosphere and our telescope. Because obviously the light goes from a star in our galaxy. I mean, here it feels very close, but of course it's still very far, right? So it still goes through our atmosphere and through the telescope in exactly the same way as the light traveling from the distant galaxy all the way to here at the end. So the problem is really the final, I don't know, kilometers or so, you know, a few kilometers. That's where all the problems are. Everything else before is fine. So the light from the star goes through the same atmosphere and telescope as the light from the galaxy. So we cannot use the shape of these stars to do any lensing. You can use them to do micro lensing, but that's something else. That's not what we're talking about here. But you don't get any information about the weak lensing from the structures outside of our galaxy with the stars.
So once we have removed the distortion from our atmosphere, to infer the distortion from weak lensing, we use mostly the moments, quadrupole moments. That is what we use to.
That's right. So we measure the moments of these, and we correct for the moments of these. So we measure the moments of this, the moment of the star, do all this method that I described, and that gives us, if we've done our work well, an estimator for the shear which is unbiased, which means that if you average over galaxies that are randomly oriented, you should get a shear.
So it means that to get the real image of the galaxy or anything, we have to remove the shear.
If you wanted, yes, if you wanted to get back to the intrinsic image of the galaxy before lensing, you need to remove the shear.
And that is the original
image
of
that you would
object.
see if there were no lensing.
Yeah. Okay.
That's right. So if you've modeled everything, if you wanted to, you could do this. Now, of course, in general, we're happy to have estimated the shear. Like, we don't go back and correct the image of the galaxy for the shear, because all we want is measure the shear. We don't really care about the actual shape of the galaxy.
Okay, yeah.
Right? But if we wanted to, we could do this.
Yeah.
So in the strong lensing I was showing you before, there people can do it can do this on a more regular basis, and then they can reconstruct the shape of the source before lensing, especially when you have multiple images. I don't know if you were there, but we had this pretzel galaxy with 4 images, and each of them you could resolve the shape of the background galaxy. And so with a proper model of the lens, you can go back and reconstruct the shape of the galaxy as you would see it if there were no lensing. So it's done more in the strong lensing case. Because in the weak lensing case, anyway, distortion is so small, by eye you can't really see a difference anyway. But you could. I mean, there's nothing wrong with that. Yeah.
Sir, we are studying structure formation by introducing perturbations on a homogeneous and isotropic FLRW.
Yes.
Can't we directly introduce inhomogeneities into the metric itself and study the evolution?
Well, that's what we do, but it's true that the way we do it is by perturbation theory. Okay, so it's true that we solve first the case where it's homogeneous, and then we add perturbations onto the metric and everything else, and then we solve for the evolution of these perturbations at linear level, or we can even go to high order. Now, what you're saying is, could we do it and solve directly everything from the beginning?
Rather take inhomogeneous.
Yeah, so that's, I mean, I think Anjan can answer, but that's much more difficult because general relativity, the Einstein's equations are nonlinear. I mean, we can talk to the relativists here in the room. They're nonlinear, and so the solution for these models are very hard to do. That's why it's usually easier to solve a problem which is easy, which is the one which is homogeneous, and do perturbation theory about it. Because then you can only keep terms to first order or second order. There are models of inhomogeneous cosmologies, but these are much harder to work with, and I'm not sure if people have tried doing full structure formation on inhomogeneous models.
The structure formation will evolve along the time itself. So we don't need to add perturbations.
That's right. So then the whole thing would evolve, but
very complicated partial differential equations which are coupled. So
yes.
Solving those are
all non-linear and
but they are very
very difficult. Very difficult.
but still you you can try.
Yeah, exactly, you can try.
Nothing wrong in it.
Yeah, you can try. People try to do, for instance, full numerical simulations with full general relativity. So even numerically it's very hard because you have a lot of fields to follow. The equations are nonlinear. It's very expensive to do in terms of computation time. I'm not sure you would gain that much, at least if GR is correct, because at early times it's all linear. So I mean, it's already, why? At late times it's nonlinear, and then.
But then you can do the Newtonian approach.
Exactly. So now there is an interesting problem related to this called the back reaction. I mean, the fact that these equations, the Einstein equations, are nonlinear means that one might worry that the formation of these structures can affect the background expansion, right? So one can question whether this expansion is valid, especially for nonlinear equations like this. And people have looked into it. And there's still work being done there, but it looks like this effect is small, but may not be negligible for future surveys.
In fact, one explanation of late time acceleration is just through this back reaction. Maybe you don't need any extra dark energy like lambda CDM or something. Then this back reaction is working in such a way that they can give somehow the effect of this acceleration. So that also, people at one point people are studying, but seems that the kind of back reaction you need, that is to get the acceleration that is not consistent with other observations.
That's right.
The back reaction to?
The back reaction of the inhomogeneity to the homogeneity.
Right. So here we solve.
You can generate negative pressure.
Yeah, you can effective negative pressure.
Exactly. That's right. Yeah. So here we solve the background. Background as saying, assuming the universe is homogeneous, we solve all these equations. That's what you've done. And then you add perturbation, and you solve the evolution of the perturbations. But what if the perturbations change also the expansion history? Because in GR, any form of energy is a source. So this perturbation of energy, so it could also influence the background expansion. And so as Anjan said, people looked at it. People thought at some point it could explain the entire acceleration that we observe and we call dark energy. But it looks like it's actually quite small. But as I said, it may not be completely negligible.
Yeah, it may not be completely.
Yeah, it's not. It's not.
Also doing still now.
Yeah, it's not. It's still ongoing. This problem. Yeah.
So is it very difficult to explain how the back reaction can give rise to acceleration?
No, it's basically what people do. You keep the back reaction, and then when you look at the homogeneous and isotropic, you have to make an average out. But you have to average out. When you average out this thing, it seems that those back reactions terms on averaging gives you a negative pressure kind of behavior. So it's not that it's actually a negative pressure, but the averaging out the back reaction can give a effective equation of state which can give you a accelerating universe.
Do you mean acceleration in some parts of the universe?
No, the overall. So that's you have to do, no? Because back reactions are basically when you get the inhomogeneity, they are local inhomogeneities, right? But then you have to make an averaging out to get the homogeneous and isotropic cosmology. When you do this, now this averaging out in cosmology is a little bit tricky issue. Whether you write down, you average out the first Einstein's equation and then you get it, or you average out for the energy momentum tensor and then you put the Einstein's equation. So whether these two things commutes, that also is not known actually. But people have tried, still people are working on it.
So, sir, weak lensing tells us about the mass distribution in the universe. So, using it, we can put some constraint on the dark matter distribution. How can we probe dark energy using weak lensing?
So I'll talk this later when I show results. But basically, as I said, dark energy affects both the geometry of the universe, so the angular diameter distance, I think you showed this, and it also affects the growth of structures. So the way, did you do the growth factor already?
Yeah, I have done the growth factor.
So if the growth factor, which is the way structures grow as a function of time, is affected by dark energy, because if you add more dark energy, you accelerate the expansion. That seems to work against gravity, and it freezes out the structures. So you slow down the rate of structures. And gravitational lensing, what it does is that it probes the way the formation of structures, but also as a function of time. So it probes both the power spectrum of the matter fluctuations, but also how it evolves as a function of time. And it's also sensitive to the angular diameter distance, because we saw that there are all these geometrical factors, ratios of distances that come in everywhere into the lensing calculations. So it's sensitive both to the effect of dark energy on the geometry, on the angular diameter distance, and also on the growth of structures. And so the power spectrum of lensing is dependent on the dark energy, the amount of dark energy, and also the equation of state. I think I showed a graph before. And so and that's how we get a handle. And it turns out that the potential constraint one can get from weak lensing on the dark energy is very strong. I'll show that later. So it turns out among the different probes, potentially, if we can get the systematics under control, the potential for constraining dark energy in that way is very strong. And that's because we can access scales, a broad range of scales. We can also do it as a function of redshift. And we can also access small scales. We can go into the nonlinear regime because we don't have this problem of bias, and we don't need to worry about the formation of galaxies and so on. I mean, there are issues there which are non-trivial, I'll talk about, like baryonic corrections and so on. But in principle, we can access a lot of modes, and that gives very strong constraint potentially on dark energy.
And maybe one fact that is the one observation where you can have both the angular diameter distance and the structure for
exactly together. And so these are very strong constraints. I mean, another way to look at it is that, this cosmic microwave background gives you a map of the radiation at last scattering plus other effects at late times. You can think about weak lensing as giving you a map, a three-dimensional map of the metric perturbations. Because what we're really sensitive to is the fact that the universe is curved because of these perturbations everywhere, right? So what we're really mapping is the metric perturbation. So it's a fundamental measurement, and these metric perturbations are sensitive to dark energy through the geometry and the growth of structures and everything, right? So it's another background, if you wish, that we're measuring. We get also three-dimensional information from it. In fact, when you think about it on very large scales, when it's still linear, these metric perturbations are coming all the way back from inflation, actually. And they're not affected by the transfer function late times. So what you really, on very large scales, you can think about it as measuring the metric perturbation generated by inflation directly. So that's quite an important measurement.
One can go with the
Well, and potentially we'll go the whole sky. Yeah, we'll do that. I mean, we're not there yet, but soon we'll get to the whole sky. Yeah, like the CMB. Yeah.
We are continuously using a phrase, different modes. What does it exactly mean? Means different mode means the different phases or different.
It means perturbation on different scales. So you can imagine if you have a big volume, like a big box, you can take a Fourier so you have a density field. So density as a function of position, function of x. You can take that box and a row of x, take a Fourier transform, and decompose that into Fourier modes. The Fourier modes are labeled by a wave number k, which goes like inverse scale, inverse length scale. And we call each of these a Fourier mode. So we call each of these the amplitude, let's say, of the lensing power at different scales. We call them the different modes. Yeah. So for a given k, for instance, the k vector has an amplitude and a three-dimension and two angles to describe its direction. And so we have all these different modes. That's what we call modes. Yeah. It's basically different the fluctuation on different scales, length scales. It's another way of putting it. But it's not only length scale, it's also direction. Yeah.
So we need dark energy to explain late time acceleration. So that back reaction explain that acceleration. Do we still need dark energy?
No, so that was one of the motivations that because dark energy you need a lot of theoretically is very challenging to model dark energy. So that was the motivation. Motivation to explain dark energy means to explain late time acceleration without having dark energy was this modification of gravity, so that you think that on large scale where this acceleration you see there the universe is not governed by Shear, but there is some modification. And the other is that there is a back reaction of the inhomogeneity that you have. So those are just to avoid the problem, the theoretical problem that we have to model dark energy.
So in 0.3, 0.7 universe, what
That means x expansion can be explained.
It means there is a
Maybe.
The
possibility.
acceleration could be.
Acceleration. Expansion is there, acceleration.
Acceleration. But now it looks like it cannot be explained fully, but it still can have effects which are significant for the measurements we're going to make. That's the current. I think status of the people working on this problem. Which is you can see the other way. I mean, it's more it makes the interpretation theoretically more complicated of the future measurements. On the other hand, it's also very interesting because these very subtle effects about the way you do averaging in cosmology or about the way you solve your Einstein equations will be observable, and maybe that can give you some interesting constraint on the theory also. Right? So it goes both ways.
So what you do now is correct lambda little bit because of the back reactions, or
That may correct lambda a little bit. I don't know. I mean, I'm not aware of those things, but I think that will actually correct.
Yeah, it would. I mean, it would basically make it deviate a little bit from lambda CDM if you did the lambda CDM with the background perturbation split that people usually do, like all of us usually do, and that was described to you. Yeah. So you would have some effective terms and everything that would be perturbations, it would be modification from the lambda CDM prediction using the background perturbation split. Yeah.
Sir, you define delta density contrast. So is it done to take out the back reaction out of the game?
No, not like that. No, why you are saying that? So
Because it's a form of average.
But there I am not doing any average. So you have a row which is now a inhomogeneous part, that's the thing. And now I have the background, rho bar, which is just function of E. And I just divided this by this. Now if I write down this, so this is rho by rho bar minus 1. Okay, so this is the way I am doing. So this is my delta actually. But this is not I am taking the average. I mean, I don't think there is any back reaction that I have taken. This is just in the fluid. You have a inhomogeneous. Now the fluid is inhomogeneous. So I do it to make a dimensionless quantity. So then it helps me to do the calculation. So I have all the dimensionless quantity that I can define from that. It is nothing to really related with the back reaction.
Yeah, other than perturbations, what type of back reaction we can consider for structural formation? Other type? We can.
Not much, because I mean the structures that what they form perturbation and density and many of the other fluid components. But
So I think that it looks like a compulsory.
I mean it needs to be looked at carefully, and as we said, there's a lot of work on this. But yeah, I mean you need to check this.
Any other questions?
So what do we do? Should I say a few words on this?
So
okay. So we thought it would be useful for me to say a few words about parameter estimation in cosmology. I briefly talked about it during the previous tutorial session when we discussed the different software packages. But I had a lot of questions on this, and anyway, it's such an integral, important part of cosmology, we thought I could say a few words. Okay? So this is the following. This relates to the following step in cosmology, right? So in cosmology, typically we have an experiment. So here I'm showing in advance some of the weak lensing measurements that are done. Okay, let's don't forget what they mean. It doesn't matter. So you have points with error bars. Okay, so the experiment, the experimental group will give you data points with error bars and the covariance matrix and everything characterizing the measurement. And then from some of the codes we described, you can get a theoretical prediction for a given cosmological model. Of course, if you change the parameters of the model, you're going to get another theoretical prediction. Okay? And the problem is, how can we use this information, the information from the experiment, the data from the experiment, and the theoretical predictions, to infer constraints on the parameters of the model? Let's say these are two parameters, doesn't matter what they are right now. and eventually you want to put contours and constraints on these parameters. Okay? And that's a problem we find everywhere in cosmology, and in particular for when you want to constrain cosmological parameters from data. All right? So the generic problem is to estimate model parameters, let's call them theta I, you may have several, typically of order 10, given a data set that we call D. So this would be the data set, the black points, and the model parameters would be some cosmological parameters, omega matter, omega lambda, whatever. Okay. All right. So there are different ways of doing it. It's, as you said, as you asked the question last time, it's a generalized fit problem. You want to fit a model to the data, but it's more general than a fit because you don't always have data points with independent data with everything Gaussian and everything, but it's basically this. It's basically that. Now, the way so different communities use different frameworks. In cosmology, we're very fond of the Bayesian approach. All right. And the Bayesian approach is based on the Bayes theorem, which is relatively simple. It states the following. So what we're interested in is the probability of the model with these parameter values given the data, right? So we're given the data, I want to say what constraint we get on the parameters of the model given the data. The bar denotes given, okay? And the theorem states, and the problem is that what we can easily compute is something different, which is the probability of the data given a model, right? So what is not hard to do is you in iCosmo or Cambo, whatever, you type the values of the parameter, you give 30% matter, 70% dark energy, whatever, and you can compute curves like this, right? Not a problem. So given the value of the parameters, and given the error bars on the data, we can calculate the probability of the data given the model. So clearly, if the theory line is up here, the probability of obtaining this data, if this model is correct, is very low. But if it fits well, then the probability is very high. And you can actually quantify that if you know the covariance matrix of the errors and the model for the errors and so on. So that quantity is called the likelihood. All right? And the different experiments, either they give you points with error bars or they actually give you a likelihood directly. Okay? So the likelihood is the one that's easy to compute, but that's not what we're interested in because we don't know which model is correct, obviously. We want the reverse. We want the probability of the model given the data. Okay? And Bayes' theorem relates the two in a very nice way, so not very hard to prove, actually. It says that this probability here, which is called the posterior, so it's a posterior probability of the model given the data, is equal to the likelihood times a prior divided by an evidence. Okay, so what does it mean? Well, what you need is these two other quantities. So the prior is the prior information you have on the model. So this could come from theoretical consideration. You can have a negative omega matter, for instance, so it certainly cannot be more negative, or things like this. You can impose universe is flat, so omega m plus omega lambda plus omega r equals 1, and so on and so on. Or it can come from earlier experiments. From earlier experiments, you may have already some constraints, and so that would go into the prior. Okay, so fine, that you can define what the prior is. And then the evidence, that's something much more subtle and kind of cumbersome, is the probability of the data. Okay, it's just the probability of measuring that in absence of a model. So obviously that's kind of difficult to estimate. The nice thing about it is that we know that any probability when integrated should integrate to 1. That's the definition of probability. So this is really, since it's independent of the parameters, this is really a normalization factor. And most of the time we can ignore it and normalize the distribution later, and then don't have to worry about where it comes. Basically try to get it from first principles. So this we usually sweep under the rug. Okay? All right, so then what we're left with is if we can have some code that calculates the likelihood of this data given the model, and we have some priors, then we can determine the posterior. Okay, and this is done routinely in cosmological experiments, and all the contours that you see, and as I already show you some, and I'll show you even more when I show you actual results, are derived, most of them are derived like this. Okay. Now the problem that we were discussing briefly I think on Tuesday, I think it was, or Wednesday, I can't remember, is the fact that in order to do this, so the goal is to estimate the posterior given the likelihood and the prior, no problem. The problem is in practice, this is not easy. Okay, it's not easy for several reasons. First of all, typically the evaluation of the likelihood, sorry, this should be the likelihood, is expensive, right? So every time you want to consider one point in this data space, in this parameter space, so let's do the parameter space like this. Let's suppose this is one of the parameters, that's the other parameters. Let's call the parameters of the model theta, so this could be omega matter, omega lambda or something. Every time one wants to calculate this likelihood on one of these, on this parameter space, it's quite expensive. It takes a lot of computational time. The second is that typically the number of dimensions of the parameter space are quite large. In the lambda CDM, there are already 6 parameters. If you extend it with including a W0 and WA, you get 8. Typically, there are systematic parameters, so nuisance parameters, one to average over. And then you can typically get to 20. And that starts to be quite a large number of dimensions. Okay? And the other reason is that typically you don't want, if you have an experiment that you're in the process of analyzing, you don't want to do this only once. You do it for a given version of the analysis, then you notice there's some problems. You change something in the pipeline, or you redo your measurement, you do it again and again. So you need to iterate and do this evaluation of the posterior many times. So if it's very slow, then that limits the number of times you can do it, which means that it limits the number of the amount of tests and correction of systematics that you can do. So really the number of times that you can do is related to how well you can address systematics. So it's very important. Okay. So initially, people did it in a straightforward way when we didn't have any, the data was small, the number of models that we consider was small and so on. Then what you can do is you can take this parameter space and make a grid. Okay, you can grid this parameter space. I don't know, you can put 20 points in this direction, 20 points in this one, 20 points in theta 3 and so on. And you can evaluate the likelihood at every point. And then evaluate the prior at every point, take the product, you get your posterior, you get this in multi-dimensions, no problem. The problem is this goes like the number of grid points that you have, which scales like a power of the dimension, clearly. So that's really, really expensive. As the number of the dimension increases, and when the likelihood estimation is slow, then this scales very badly. It's too slow. So then people introduced, and the people who introduced it the first, at least in the first way it has a big of impact, was Anthony Lewis and Sarah Bridle 2002, is that they said, let's use Monte Carlo Markov chain methods to solve this problem. And now Monte Carlo Markov chains are used widely in cosmology. There are also other methods that are used as well. But this one is used very, very broadly. And the idea is the following. Instead of evaluating the likelihood or the posterior on the grid, one generates samples, so points, in this parameter space, which are distributed. So there's an algorithm to generate points or samples in this parameter space, which are distributed like the likelihood or the posterior. It doesn't matter. So let's say the likelihood, okay? Or the posterior. So basically, you have an algorithm that instead of having to look at another grid, it moves points around until these random points have a density which is proportional to the posterior probability that you want. Okay? And then once you have that, you only have to, the advantage of this is that after a while you only need to sample and to calculate the posterior where the posterior is large. You don't have to worry about the other places which are where the posterior probability is very low. So it's much more efficient. And then if you need more precision, you just increase the number of points.